Hey everyone, welcome to the video. This is the first video of a series of videos that I'm planning to do called Paper Bits. The idea of Paper Bits is to discuss small, bit-sized pieces of interesting results from top theoretical computer science conferences such as SODA, Stock, Fox, and others. In this video, we'll be discussing a result from SODA 1999 in a paper called Multi-Level Adaptive Hashing by Andre Broder and Professor Anna Carlin. I'm also going to be referencing some results from Professor Serial's lecture notes called The Power of Two Choices. In fact, I first came across this problem in one of his assignment problems in a course that he is teaching that I'm currently taking. I'll leave a link in the description to both the SODA paper and the Power of Two Choices lecture notes. The video will require some prior understanding of some basic probability theory like random variables, expectation, and linearity of expectation. So I highly recommend brushing up on these topics before watching the video if you don't remember them already. And with those caveats in mind, let's get started. Suppose we play a game where I randomly and independently throw n balls into n bins. I look at the balls contained in bins alone, and I delete them. The rest of the balls survive this round and go on to the next round, where again I throw them into n bins. I keep repeating this process until no ball remains. The question is, how many rounds does it take for this game to finish on expectation? Let's take a more concrete example. Suppose we start with 10 balls and 10 bins. In the first round, I throw each ball independently into one of the bins as shown. I look at balls that were alone and delete them. The rest of the balls survive this round and pass on to the next round where I again throw them into 10 bins. This time, only 2 balls survive. Finally, in the third round, I throw the 2 balls and they land in different bins, so I delete them both, and with that, the game ends as there are no more balls. This game took 3 rounds to finish. Now, analyzing this game in one go is a bit too hard, so let's focus a bit on just the first round. How many balls usually survive the first round? Well, one way we can think about it is to repetitively throw 10 balls into 10 bins and see how many survive in each trial. We repeat this process thousands of times and plot a histogram of the number of balls that survive in the first round across different trials. Here's the histogram of the number of surviving balls with n equals 15, n equals 100, and n equal 150. You'll notice something very interesting. The number of balls that pass on to the second round has a typical bell shape, and in addition, the number is extremely concentrated around its expectation. But again, how do we even calculate that expectation in the first place? Here's one way to do the analysis. Suppose we instead throw m balls into n bins. How many balls do we expect to survive? Well, let's set an indicator variable xi, which is 1 if ball I does not survive, and 0 if it survives. Then the expectation of xi is simply the probability that ball I does not survive, or probability of xi equals 1, which is n minus 1 over n to the power of m minus 1. To see why, consider the bin that ball I falls in. For ball I not to survive, we must have that all the other m-1 balls avoid the bucket that ball I fell in. But this happens with probability n-1 over n for each of those m-1 balls. And since the balls are independent, then we just multiply these probabilities. So, using linearity of expectation, the expected number of balls that do not survive is m times 1 minus 1 over n to the power of m minus 1. And so the number of balls that do survive is just m minus the expected number that don't survive, or m times 1 minus 1 minus 1 over n to the power of m minus 1. That was a handful. Now let's do a sanity check and make sure that this is the right formula. Let's plug into the formula m equals n equals 30 and we get something around 19, which is approximately where the expectation of our simulation was. Great, so it looks like the equation is right. Now remember, from the numerical examples we showed, we noticed that the number of balls that survive is strongly concentrated around the expectation we just calculated. It turns out that we can prove that this is true using a martingale inequality, which is called Asima's inequality. The inequality is slightly outside the scope of this video, so I'll skip the details, but definitely feel free to research it if it sounds interesting. So in our analysis, we will assume some assumption, mainly that the number of balls that goes from one round to the next round is exactly the expectation. This is not a completely absurd assumption because of Asima's inequality, but it simplifies the analysis a lot. However, you don't really have to do this assumption, and I urge you to look at Sariel's lecture notes or the SOTA paper for a more rigorous analysis. Alright, with that out of the way, we're now ready to analyze how fast this game finishes. To do this, we'll set up a recurrence. We will let xi denote the number of balls still alive in round I. Using our assumption, we get the recurrence xi plus 1 is equal to xi times 1 minus 1 minus 1 over n to the power of x minus 1 by simply subbing in the expectation equations from the last round survivor and a base case of x0 equals n, since we start with n balls. Note that xi is just the number of survivors from round I, which we assumed is expectation. Our goal is now to find the minimum I star such that xi star, or the number of survivors in round I star, is less than 1, or no more survivors. In the analysis of this recurrence, we will need two very useful inequalities. The first is a very popular inequality called the exponential inequality, which just states that 1 minus 1 over n to the power of n minus 1 is at least 1 over e for n greater than or equal to 1. The second inequality is called Bernoulli's inequality, and states that 1 plus x to the power of r is at least 1 plus xr for x at least negative 1. Using these two inequalities, we will get two different bounds for xi. The first uses the exponential inequality. We have that xi plus 1 is equal to xi times 1 minus 1 over n to the power of xi minus 1. But since xi is at most n, then this is at most xi times 1 minus 1 over n to the power of n minus 1, which, using the exponential inequality, is at most 1 minus 1 over e times xi. This is now useful because we can unroll this recurrence to get xi plus 1 is at most 1 minus 1 over e times xi, which is at most 1 minus 1 over e squared times xi minus 1, and so on until x0 equals n. So we get the final bound of xi plus 1 is at most 1 minus 1 over e to the power of I times n. The second bound we will use Bernoulli's inequality. We have that 1 minus 1 over n to the power of xi minus 1 is at least 1 minus xi minus 1 over n using Bernoulli's inequality, which just simplifies to xi times xi minus 1 over n, which is at most xi squared over n. Great! We now have two inequalities to bound the speed of conversions of xi, shown here. Now, what happens after log n plus 1 rounds? Well, using our first bound and a bit of algebra, we have that x ceiling log n plus 1 is at most n to the power of 1 minus log e minus 1 times log n over log n. I know this is a handful, but working through the algebra, this should be the result you get. What about round log n plus 2? Well, now we start using the second bound because it gives us faster conversions. Subbing the upper bound we got for x log n plus 1, and we get n to the power of 1 minus 2 times 1 minus log e minus 1 times log n over log n. Repeating this for x log n plus 3, x log n plus 4, and you start seeing a pattern. After an additional t prime rounds, we get that x log n plus t prime plus 1 is at most 1, as shown in the algebra here. But ceiling of log n is O log n, and t prime is also O log n, so after O log n rounds, this game ends. Now, the natural question to ask is this bound tight? Well, it turns out that yes, you need omega log n rounds to finish the game. I'll leave that as an exercise for you to try, but you'll need the inequalities 1 minus e to the power of negative 2x is at least x for x at most half, and 1 minus x is at most e to the x for all x. The proof idea is similar. You just need to show that after, say, log n minus 10 rounds, xi is still greater than 1, and so the game cannot have been finished. But these bounds imply that this game needs theta log n rounds to finish. What's even more surprising is that without the expectation assumption we did, it still takes theta log n rounds to finish with high probability. For more details, see the lecture notes or the SODA paper. Now, why is this game useful? Well, it turns out that this is super useful for hashing. Instead of the classical way we hash one element into one bit and getting a lot of collisions, we can instead hash them into theta log n different bins, each of length n. We can simulate the game to hash n items until they belong into one bucket without any collision, which we argued would happen with high probability in at most theta log n rounds. This immediately gives us a hashing theorem of hashing n items into n bins, with an additional memory of just theta log n extra space, we can get with high probability that there is no collisions. Thank you for watching the video, and special thanks to everyone who helped me prepare this video or gave me feedback. If you liked the video and would like to see more, please feel free to like and subscribe to the channel, and I'll see you in the next video.